Hi everyone. In this video, we will cover how to implement a multi-layer perceptron classifier from scratch using just Numpy. Now first, I will go over why we want to go through this exercise and then outline the exact architecture of the model that we will construct here. Next, we will jump into a Jupyter notebook and actually build an implementation of our neural network and then test it on a simple dataset. Now, all coding shown in this video is available in a Jupyter notebook available on my GitHub. You can find a link to this notebook in the description below. So why might we want to build a neural network from scratch? After all, we have various different frameworks to choose from, such as TensorFlow, PyTorch, Keras, that really simplify our task of building neural networks without having to dive into all the details. Well, it's precisely knowing these details that motivates us to build a neural network from scratch. If we want to get beyond just surface level knowledge for how these algorithms work, we want to be able to take the mathematics that describes how a neural network should be able to learn and implement that into code and then actually test and see the resulting implementation actually functions. So that's our motivation for why we want to go through this exercise. Now, let's cover exactly the type of model that we will build here. So here you can see a figure for the neural network that we will build. It is a feed-forward neural network classifier involving three different layers. So we have an input layer, we have a single hidden layer, and then an output layer. Now, we will make a few simplifying assumptions that will make our implementation that much easier. So the first is that we will only have these three layers, and the activation functions involved for the hidden layer and the output layer will be sigmoid activations. So that will just simplify our calculations later on of the various derivatives we will need when implementing backpropagation. On top of that, the number of neurons per layer are as follows. So the input layer will have 3 neurons, the hidden layer will have 5 neurons, and then the output layer will have a single neuron. Now, this network is going to be implemented to tackle binary classification problems. And as such, the activation on our output layer will be a sigmoid as well. That can work. Now, our general approach for the training procedure for this network will be as follows. We are going to iterate through an arbitrary number of epochs. Now, an epoch just involves applying all the training data that we have available to our network in order to update the weights in the model based on the data we have. So for each epoch, we are going to do a forward pass. So that means we're just sending the data from our input layer through to the output layer. We are then going to do a backward pass, and that involves computing derivatives from the output layer back towards the input layer. And then we update the model weights based on the derivatives that we've computed. Now, because this is going to be a binary classification problem, the loss function we will use here is cross entropy, and it will have this following form. Now, because of this choice of loss function, we just have to make note of a couple things. So when doing our backward pass, more specifically when initiating our backward pass, the derivatives we will use for our loss function with respect to our prediction value will be as follows. So it will be this logarithmic function, and then the derivative of the activation function in our output layer with respect to the input z will be of this form. So these are just some things to make note of. If you want to dive into the details of how backpropagation works, I have an article on this topic on my blog. You can find a link to that in the description below. So yet another simplifying assumption we'll make here is that we will make use of backpropagation with batch gradient descent. And this means that we will apply all our data at once during each epoch in order to update the weights a single time. So that means that the number of passes we have to go through the network just equals the number of epochs we have. So this just simplifies our task. Now, to do a prediction, once we have a trained model, this just involves doing a single forward pass, and then we just get our predictions at the end. So this outlines just our general procedure for what we will do. We can now jump into a Jupyter notebook to implement our algorithm. So now we're in a Jupyter notebook, and we can begin the implementation of our neural network. So the first cell I'm going to run here will just import all the functions that we will need to make use of. And now we will work through the implementation of our neural network. Now in the notebook here, I've just listed out the 3 key assumptions that I've already mentioned in the previous part of this video. And now we can begin our neural network implementation. So the whole algorithm is going to be encapsulated in a single class. It is going to be called MLP351 classifier. And now let's just walk through each of the member functions of this class. So the first is the initializer, and the initializer is just going to set up all the member variables of the class when we create an instance. So this includes setting the learning rate. We have the number of epochs, and both of these parameters are actually inputs to the initializer. We then set the number of layers, and here I've hard-coded them to be 3, 5, and 1 for the input, hidden, and output layers respectively. I then leave empty lists to contain the model weights, the biases for each of the neurons, and then the loss function values. So this is our initializer. Correspondingly, I also have a destructor implemented, and this is just to clean up everything after an instance is removed. And so this just basically deletes all the member variables that I just walked through in the initializer. So that's what these 2 functions are doing. The next function right here defines our loss. And as mentioned before, we are using a cross-entropy loss here. And so this loss function just takes in 2 arguments. It takes in an array of our true label values and then the predicted label values. And then we basically just have a single line here where we compute the cross entropy and return it for these 2 arrays. So that's what the loss function is going to do. We then compute the derivative of the loss function, and this is the logarithmic equation that I mentioned in the previous part of the video. So here we're just computing the derivative of the loss at the output layer. The next member function we have is just called sigmoid, and this is just computing the sigmoid activation function for our hidden and output layers. So this just takes in an input z, and the z value is assumed to be a dot product between the weights of that neuron and the inputs to the neuron plus the biases that are associated with the neuron. So that's z, and then we just compute the sigmoid activation function on it and return that value. The next member function we have here is simply computing the derivative of the sigmoid activation function. And this will be useful when we do our backward pass through the network to compute all the various derivatives we need in order to update our weights. And now we get into the member function to compute the forward pass. And so that's all of this here. We pass in an array called X, and this contains all the input features for this pass through the network. And then we start by setting up our variables at our input layer. So our input layer just involves making a copy of the input data, and then we set our activations and our derivatives at this layer. So that's simply what we are doing here. And then we move on to our hidden layer. So that's this block of code. Now here we take the data that we receive at the input layer, we multiply it by the weights that are associated with the hidden layer, and then we also add on the biases, and this gives us our Z values, and then these Z values can be passed on to the sigmoid function to get the output from this layer. So that's what we then get here as input to layer. We then add this input to layer to our list of activation functions, and then we also compute the derivatives and also store that in our list called derivatives. So here we're keeping track of both all the activations and derivatives as we move forward through the network. Next, we now move on to our output layer. So that's then our next block of code, and we basically repeat what we did previously. So we multiply the weights for our output layer with respect to what we have received from the hidden layer, and we add the biases associated with our output layer. So the result of this calculation is then fed into the sigmoid activation function again. We again update our variable input to layer, and then we store the input to layer to our activations list, as well as compute the derivative again and store that in derivatives. And so the result that we get from this function is a tuple containing two lists. It's the list of all our activations and a list containing all the derivatives associated with those activations. Now we can move on to our backward pass. And so the next function we have here, outlining it here, is as follows. So it takes in 3 arguments. The first 2 are the lists that we just talked about during our forward pass. So it's the list of activations and the list of derivatives. And then also we pass in y, and this is just the array of true target values for the training data we have. So these are the values that we're passing in. So the first thing that we do for a backward pass is we compute our loss using the cross entropy, and we record it to this list called loss. So that's all we're doing in the first line. Then we compute the derivatives we need for our output layer. So what are we doing here? We compute the derivative of the loss with respect to the predicted value at the output layer. So that's we're calling the function derivative loss. And then we multiply this derivative with respect to the last derivative that we got from our output layer. So that's what we have stored in our derivatives array. So we're multiplying these two, and this yields to us the derivative of the loss function with respect to the Z input value to the output layer. That's what we get here. We then perform yet another matrix multiplication again, and we take the derivative we just computed and multiply it by the activation function from the hidden layer, and this gives us the derivative of the loss with respect to the weights in the output layer. So that's what we get here. And then we can do this computation at the bottom where we just sum over the derivatives of the loss with respect to Z2. Z2 is the Z value from our output layer. And this gives us the derivative of the loss with respect to the biases available in our output layer. So now the key thing that we get out of this block of code are the derivatives of our loss with respect to the weights, that's W2, from our output layer, so that's what this is associated with. And then we also get the derivatives of our loss with respect to the biases from our output layer, that's B2. So that's what we're getting from this block of code. And then we basically repeat this calculation for the hidden layer. So that's what this next block of code does. We do a matrix multiplication of the weights that we have in the hidden layer, and we multiply those by the derivatives we have of the loss function with respect to the Z value for our output layer. That's what we get here. And this yields the derivative of the loss with respect to the output from our hidden layer. And that's Y1. So Y1 is the output going from the hidden layer to the output layer. This is what we compute here. The next calculation we do is a multiplication between this derivative, the loss with respect to Y1, and we multiply that by the derivatives that we stored during our forward pass for the hidden layer. And that's what we have here. And this yields to us the derivative of the loss with respect to Z1. Z1 is the input to our activation function in our hidden layer. And now with this derivative, we can apply it below, and we can then use this calculation to get the derivative of the loss with respect to the weights in our hidden layer. So that's W1. We do that by doing this matrix multiplication of the derivative we computed in the last line, and we multiply that with the activations from our input layer. So we have that here. And like before, we can compute the derivative of the loss with respect to the biases in our hidden layer by summing over the derivative of the loss with respect to Z1. So that's what we're doing in this final step. And so now we've gone through these two steps. We've computed the derivatives for the hidden and the output layer, and we can return these then at the end in these two lists. So that's what we have as output here. And now we can define yet another member function, and this is just taking the derivatives that we computed during our backward pass, and we use it to update our weights and our biases. So that's all we're doing here. And we use a learning rate here to control how fast we make changes to these model parameters. So that's what LR is doing. So these are the key functions, and now we can put these all together in order to build a training method for this neural network. So that's what we do next in fit. So fit takes in our training data that consists of X, and this is our set of input features, and Y, which is our true labels. And then what we do is first we initialize the weights, the biases, and the loss values, and we just clear those so that we can have a fresh start. And we begin by iterating through all the different layers we have in the network, and we initialize the weights and the biases. And we just do that with a random number generator. We just set them to small values, but they need to be initialized in this way to ensure that the gradient descent algorithm functions properly. So that's what we're doing with this block of code. And now we just run through all our different epochs and we do our forward pass. We then take our activations and the derivatives computed and we pass them through to our backward pass that follows up, and then we update our weights. So this is just our procedure, and we iterate through as many epochs as we need in order to get a good training on our data. So that's our whole training procedure. And finally, we implement also a predict method, and this just takes in a set of input features, X, and we just do a forward pass. We get the activations out. We don't need the derivatives in this case, and we just round our activations in our final output layer and return those. And that's the whole implementation for our network. So let's run this cell, and now we can create a data set, and this is going to be just a simple toy data set using the make classification function from scikit-learn. This function is going to consist of 10,000 samples. We're going to have 3 features, and this makes sense because our input layer is just defined to have 3 neurons. Of these features, only 2 will be informative, and the third one will be redundant. And I'm also setting the random state so we can have reproducible results. So let's run this, and we can generate a plot of our predictor features. And here we see the rough distributions. We can see that their distributions differ a bit. The second and third features seem to be more or less zero-centered, whereas the first one deviates a bit. And there's also the presence of more outliers within the second and third features as well. And so we can also make a histogram plot of the true labels, and we can see here that they are pretty fairly balanced. So that's good to see. And now we will do a simple train test split. In this case, I will save 20% of the data for testing. And again, I'm setting the random state just so we have reproducible results. All right, now to test out our implementation, we can create an instance of our neural network. I'm going to set the learning rate to be equal to 1, and we're going to use 2,000 epochs during training. Afterwards, we will pass in the training data to our fit method to train it right away. And so now let's plot our loss to see how the model has learned over all the epochs that we have applied for this neural network. Okay, and we can see that there's a steep drop off in the loss values right at the beginning. Then this sort of plateaus out, but it continues and then kind of flatlines after about, say, 1,000 epochs or so. And it continues to go down, but the main decrease has already occurred after 1,000 epochs. Okay, so this at least looks good. It shows that our model is actually converging towards a solution. So we can generate some predictions and then actually test and see how well the neural network has actually done. So let's do this. Generate our predictions, and now we can see that the neural network has an accuracy of 93% and also achieves an F1 score also of 93%. So this indicates that our model is working and it's done a fairly reasonable job on the data. So that's great. It shows that our implementation is actually functioning. So this concludes the video. I hope you learned something by walking through this exercise with me. If you enjoy this content, please like, share, and consider subscribing to the channel. Your support is greatly appreciated. Have a great day, and see you in the next video.